This talk is about using and improving digital tools for robot learning and benchmarking. Here is a recent paper, Any2Track, one of the best humanoid whole body control papers, all trained in simulation. Okay, so this is what happens right now in locomotion. This is one of the coolest demos you can see. However, for manipulation, the coolest demo is this, which is also looks pretty nice, but this was trained very differently. This is trained using learning from demonstrations in the real world. So in locomotion, all the learning happens in a simulation, in a physics engine, while for manipulation, we're crowdsourcing a lot of demonstrations through teleoperation, which is very costly, and it is only possible to few, companies with lots of resources or to very, very few academic labs, if any. So the question is, of course, can we do the same revolution using simulation for locomotion? Can we extend this to manipulation, of course, right? And simulation is a powerful alternative. These are different algorithms from graphics researchers that, they publish their paper and then they put in their GitHub. And because each one saves the algorithm in their GitHub, we cannot use it to train robots, right? Because when we train robots, we download a ready simulator like Isaac Lab or and so on. So despite the fact that the tools are there to really bring the real world in a physics engine, the engineering effort is not there yet to collect these efforts in the same place for robot training. So Xianzhu here is one PhD student of mine that led the Genesis physics engine. Is a new physics engine that was released in December that puts in the same place a lot of physics solvers written from scratch in Tai Chi, a GPU parallelizable programming language. You can do rigid, liquid, gas, deformable objects, thin shell objects, granular objects, all in the same place. It's very fast, especially for piecewise articulated scenes, faster than the Mujoko, the GPU version of Mujoko. You can see here, you can interface liquid with rigid, and these soft objects with rigid objects, and deformables with water and the articulated robot hand. And the question is, we have this platform and we want to use it for robot learning and robot benchmarking, as I'm going to show in a little bit. But the platform is not enough. We need to, to be able to use the simulator, and actually Manolis discussed about that these beautiful benchmarks that he introduced in the community. There is insane amount of time put by experts, right, the designers, to make the assets and the scene and things to look good and things to be in the right place. And the question is, can machine learning help us in that direction? Going all the way from generating the assets, putting it together in scenes, designing the tasks, the reward functions, the training of the robot and so on, all the way. Like, can we automate all this pipeline to have robots that are trained in simulation? So I'm going to touch on few steps of this pipeline. First of all, what about 3D assets? Well, right now, since 2023, when this started, right, we have the power to convert any 2D image in the corresponding 3D model using, versions of Dream Fusion, right, by using view-conditioned image generative models. Then we can query their physics properties from language models or visual language models and their size. And you see here the pumpkin is larger, let's say, than the pepper, despite the fact that in the 2D image crop this information is not there. This is the latest, some of the latest and greatest of image to mesh models. These are also open source from Huiyuan company, right, the startup. What can you do with those models? Well, you can take an image of a shoe and make a 3D mesh of a shoe, put in the simulation, and this will allow you to train your robot to pick and place the shoe. You won't be able to tie the laces of the shoe because this is still a rigid mesh, right? That's the problem. So the next stage will go from these single monolithic objects to part-based reconstruction and physics estimation of those assets. So this is where we want to go. So one tiny step in that direction is this paper we have that is going to show up in EURIPS 2025. So what Parkrafter does, very similar to the previous model with the shoe that I showed, it takes a prompt and image, but instead of generating the mesh of the object, it generates multiple meshes together. Okay, so it jointly denoises multiple meshes of K objects, and K is hyperparameter given as input to the algorithm. So I'll give you a small description of how this works. The amazing technology behind this generative models that go from image crop to meshes is this latent diffusion, which means denoising in the latent space of those 3D assets. First, we train an VAE that maps a mesh into a set of latent vectors, which I'm going to describe how this is done. And then what we do is we take those latent vectors, we add noise, and then we denoise them. Okay, this is essentially what happens. Often to do that, we also take some prompt. Otherwise, if you don't take any prompt, this means that as you denoise, as you sample from your generative model, you'll get chairs or tables and so on. So we feed a prompt that tells us what is the image of that asset. Okay, so we feed the GLIP or dino feature of those in the different layers of that latent diffusion. Okay, so this is how this works. So the latent diffusion is just a diffusion transformer, basically. But the VAE, I feel, is pretty interesting. So what happens is you take your mesh, you sample surface points, then you subsample those surface points and you featureize them by cross attention to the whole set of points. And then you do cross attention to them, and these set of latents, which essentially correspond to points in your mesh, in the surface of your mesh, this is the latent, essentially the bottleneck of your VAE. So you have your set of latents, each one corresponding to a point and its feature vector. And then what the decoder does is it takes query points as XYZ coordinates and then featureizes those XYZ coordinates, fuses information with the point latents that I said to predict a value between 0 and 1, which is the occupancy of this query point. And in this way, you can decode, whole meshes, like continuous values. You don't need to go through voxelization and to have some very ugly, result. You can have continuous resolution in your output. So this is the VAE, and it's incredible and has been trained in the lots and lots of observers meshes, and has been trained on object level. So now we're going to go to part level, and what we found is that we don't need to retrain that VAE. In the same way it can do very well on auto-encoding whole objects, it does very well on auto-encoding parts. So the only thing we're going to do is we're going to take that latent diffusion model, okay, that essentially takes one set of latents, as I said, and denoises them through lots of attention layers and attention to the crop. And instead, we're going to do it compositional. We're going to make the latent space compositional, which means instead of having just one set of latents, we're going to have a multiple set of latents where each set corresponds to a different part. And here we have two parts, the dragon and this other purple thing, which may be the wings of the dragon. Okay, so you can have lots of parts, but this is what we're trying to explain. So now you just instantiate multiple point latents, and each one has been produced by encoding the different part mesh. And then in that denoising transformer, okay, we're going to essentially copy paste the weights. We're going to initialize from the weights of that image to object model that has been trained. It has 4 billion parameters, has been trained from a lot of examples. So very much we want to reuse its knowledge. So essentially now we are having some attentions within the part latents and some cross attentions across the part latents. And then we decode the denoised set of latents by replicating the VAE decoder across parts. So essentially, the same technology that was operating at object level now operates at part level, but there is also the cross-part attention so that we can fuse information across parts. That's the idea here. Why I like this architecture? Because essentially what it does is it takes an image and it does joint segmentation and reconstruction. It jointly segments and reconstructs what we see in the picture. And here is a method that doesn't do joint segmentation reconstruction. This is our baseline, which first segments an image, as you see, with the binary masks, and then feeds those to a model to reconstruct that part. And there is a limitation in this method because you can only reconstruct parts that you see right now in your image. But there are parts, for example, my legs exist, but you cannot see them right now. So such a segment then reconstruct approach will not be able to generate the parts that you actually don't see, okay? So we don't do that. We just take the image prompt and attend to it, and that the parts figure out how to split the image into different part meshes through, large-scale training. So where we found the data to train this model, we went to Objaverse, and in Objaverse there is information about parts that is often thrown away by these whole object methods. And we found part annotations. We found 50K part labeled 3D objects. And I want to mention that this was led by Yuchen Lin, excellent student from Peking University. So he is the first author here in this work. So we generated that data. I showed you this earlier. We jointly denoise the meshes, and here are some results. So here is the image prompt of that car, and then we generate, so under the hours is our method, and then we split them. So you see here we generate 4 wheels, despite the fact that not all 4 of them are visible. And the same thing you can do for whole scenes. So now we take an image of a scene and we generate tons of parts jointly, and so on and so forth. So this code is available online, and of course we want to push this to as a way of going all the way from images to scenes. And I really enjoyed the previous talk because, there are multiple ways you can do that through more symbolic methods or through these end-to-end generative models, let's say. Okay. So the last part of the talk is about where are we right now on this pipeline of going all the way from videos to simulations. This is our work, Robot Arena Infinity, which will be on archive this week, that is about scalable robot benchmarking via real-to-sim translation. So this work was done primarily by Yash, Yi, Dikashu, and Chen Yu, that are joint first authors here. The motivation is as follows. We keep having more foundation vision language action models coming out on Twitter, and we don't have a good way to compare them and really evaluate their generalization. And in some works, it's obvious, the generalization is obvious. Like when you have a humanoid that you kick it and push it like hell and it doesn't fall, you know that it works. But in these VLAs, this is not the case. The robot is on its own, nobody disturbs it, and so on. It's not really very extensive, the demos that are being shown. And this for good reason. It's hard to evaluate robot policies. What happens, actually, you need to go in the real world and do manual resets of the scene again and again and again for your own model, as well as for each one of the baselines. And then you need to trust your student that is going to have accurate assessment of your task success for your own robot policy as well for the baselines. And this is extremely subjective. Now, there are simulation benchmarks, but these simulation benchmarks you train and test inside a very closed and limited domain. So they are not really, easy to evaluate robot generalists trained with outside data. Often specialists that are trained with tiny amount of data may do better, but this doesn't mean that they can scale outside of that closed world of that simulated environment. We are very inspired. The question of evaluation is not unique to robotics. The same holds for language models and visual language models. How can we evaluate them? And there is this language model arena work from Berkeley that we are very inspired by that say the following. We're going to evaluate them by crowdsourcing human preference data. So human users that are going to be the final consumers of this technology will put tasks. So here you see if yx is the solution, differential equation, blah, blah, blah. This is a pretty intelligent human user that put that task. Then this task is fed into 2 language models without revealing their identity to the user. The user sees 2 answers, and then it casts a preference which one it prefers. And each language model is trained on a different data. So our idea here is that we want to do the same thing for robot policies. Okay, can we have tasks and then crowdsource human preference on execution videos? So how can we do that? Well, first of all, the only way we can see this scaling up across tons and tons of tasks which are necessary, because as the abilities of robot generalists expand, their evaluation of those abilities requires a growing, set of tasks to really validate their abilities and point out their failures. So this whole thing is going to be conducted in simulation. So what we're going to do is we're going to find a way to automatically convert videos into simulated arenas. And the reason we're converting actual robot videos to arenas instead of just going in the simulation and crafting our own environments like Manolis presented earlier is that there is an incredible work from Stanford called Behavior, where they have put a huge manual effort on making 1,000 tasks for robots in simulation, very photorealistic environments and very physically plausible, and all robot policies score 0 on that benchmark because the robot policy's current competence is really not, evolved yet. Okay, so for language models, if you make a language model get confused, you write a paper about it. But for robot policies, the default is that they don't work. So the question is, how can you make a benchmark that is not going to be 0, that will still be able to differentiate the current VLAs and actually follow the progress in the field? So we can have hard tasks, but we can also have easier tasks. And one way we thought to do that is by bringing that benchmark closer to the training set of those policies. And the training set of those policies is actually those OpenX embodiment datasets. Okay. So here is what happened. So the hard part in this work was this real to sim translation. And one of the hardest part of that real to sim translation was camera robot calibration. So we see the video, we know what robot is being used, let's say UR5, we take the URDF of that robot and we put in our simulation environment, and then we need to decide where to put the cameras, okay? And oftentimes, these cameras, the benchmark is not calibrated, so it doesn't tell us where to put it, so we need to infer it ourselves. So we do this with differentiable rendering. First, we go in simulation, and we train for each robot this neural network that maps the pose of the robot, meaning the joint angles, to 3D Gaussians, that if you render them, you'll see the correct, robot pictures, all right, from different views. So you train this in simulation with differentiable rendering, okay? You generate the Gaussians, render them, get loss and backpropagate, and then you freeze that model, and then you optimize for the placement of the camera, the rotation translation of the camera, by rendering again those 3D robot Gaussians and matching them with the video. And you can see in the beginning, it's totally not well calibrated. And then as the optimization continues, eventually, you put the camera in the right place so that if you render the robot, it exactly matches the video. So now we have placed the camera correctly, okay? And the next thing is we segment the objects using Gemini and label them and 3D reconstruct them with Hongyuan 2.0, and eventually we want to put our own models here that do part-based reconstructions, okay? And then we ask Gemini for physics properties so that if we put them in a physics engine, those assets will behave correctly. And right now, what we do is we take the background image where we have removed the robot and the objects and we paint it. But in our current work, we make this complete 3D, full 3D. Now, this is just a fake poster on the background. In our next version of Robot Arena, there's going to be a full 3D scene. And this is very important if you want your robot to move or to have wrist cameras, okay? And because this image to 3D mesh models reconstruct the objects in canonical orientation, you need to estimate the pose of the objects to place them in the right scene. So that's it. And this brings everything together. So you go now from a video to the corresponding simulated scene. And you also need to adjust for the PD robot gains between the reality and your simulation environment so that, the robot essentially moves in a predictable way. What we do next is we have two ways to score the robot videos. One is using visual language models and the other is using human preferences. For VLMs, we just prompt them with some shuffled video sequence and we ask it to predict the task progress and is actually doing well. This is our videos from our Robot Arena benchmark. So you see some are derived from the bridge dataset, some from droids, some from RH20T, and so on. And we're ready now to deploy robot policies on them. And we picked 4 robot policies because they don't use wrist cameras. And this is CogAct, RoboVLM, Special VLA, and Octo. So we deploy them in the environment and we get those execution videos, okay? And then we go on our web interface and hire, workers, and we show them execution videos and they need to cast preferences. Okay. And this is what the VLMs suggest about how those VLAs can be scored, so can be ranked. So they rank RoboVLM and CogAct higher than Octo and Spatial VLA, and their performance is much higher in Bridge than in Droid and RH20TC. And this is how the humans like those models. And you see there is agreement between what Gemini likes and what humans like, which is helpful. Now, you can also see here the lack of generalization. Whatever has been trained on Bridge does not generalize on Droid or on other environment. Okay, so basically we clearly see like a little bit of a kind of over exaggerated, generalization when there isn't in those VLAs. You also can do perturbations in your scenes because you're in a simulation to really stress test the abilities of those policies. And you see that, the performance drops once you do these perturbations, you change the background scene, and you change the locations of the objects and so on. So the takeaways is that simulation can help us benchmark robot policies trained on anything, each one on their own training data. We start close to the training data, but we keep expanding. Actually, you want to be a continually evolving benchmark. You don't want this to be a static benchmark, so we're working on that direction. And generative models and VLMs, and this is the whole point of this workshop, can help us do this generation of simulated worlds, much like also Manolis described, and they keep getting better, so they keep assisting us on building better, essentially, robot benchmarks. So thank you very much for your attention, and I'm happy to take questions.
Thank you for the great talk. I think there's a big gap between what you showed from the Genesis simulator and this last piece of work. And so I was wondering, what you're doing now is keeping up with the current state of the art with DLA models, doing also not too dexterous manipulation. What are your thoughts as we move towards more dexterous and deformable objects? How are you thinking about how to get those into sort of the simulated environments for evaluation?
Yeah, so basically what you're saying is that your environments are all rigid, right? While you're showing some nice cloth and deformables in the pictures, right? Yeah, a very good point. So unfortunately, the physics solvers were not ready. When we were developing that benchmark, the physics solvers for deformable objects were not ready, but now they are. So the next generation of the benchmark will have soft objects and water on the glasses and so on and so forth. Yes, absolutely, this is what we want to do. Mm-hmm. Thank you for your question. Yeah, you're absolutely right. Yeah.
Thanks for the great talk. You mentioned this kind of continuous evolution of the benchmark data set.
Mm-hmm.
It's really important that there's of course two sides, right? The real, right, taking data from the real world and using that, and also the synthetic, right, the instruction. Do you think there's an ordering that we should use?
Very good.
Sort of preference?
Great. Yeah, this is a great question. So here is where our vision is what we want to go. In the same way that in LM Arena, the user shows up and puts a task down and says, this is what I'm asked, my question is. We want the user to come and say, I want the robot to stack 10 plates here on this picture of the kitchen. So you show me the picture of your own kitchen. You say, I stack plates, and I say, okay, here is the environment I make. Do you like that? You say, no, make wider plates. Make also some smaller plates. And then first we jointly design the task, because right now it's really boring. Like, we give them the execution videos and they need to cast preferences. We want the user to come and tell us the task. And then we use these fantastic tools from this workshop to make the scene, okay? And then we, run our VLAs and then we score them. Yeah, so this is where we want to go. And now that's why I was asking you also the previous question, once the user describes the task in text probably and shows a picture, we can use code, or we can use text-to-image models, or any combination of the two to be able to do that. And we're very excited about this direction. Yeah, thank you for your question. Yes?
Let's go. You showed examples where a chair was broken down into its constituent legs, armrests, etc. And also examples where you had a full scene where that chair would now be one part of the full scene.
Yeah.
What's your view on how to reconcile those two kind of different views of a hierarchy of composition, scene level and object level? Do you believe maybe compatibility, or how would you reconcile this to one?
Yes, this is a great question. So what is an object in one scene and task is a texture in another scene and task, right? So if you go in the market and you see, thousands of bananas, you don't care about, you care about the texture. So it's all about task specific. Also, in this model, you can also prompt it with text. Okay, segment such and such parts. This is totally possible. You just need to inject this language at training time. And I think this is the right thing to do. And then the brain thinks, VLMs are very good on figuring out the relevant objects and parts. And then you feed this into the model and then you focus its reconstruction. Because reconstructing on the finer level of detail, I think it's totally impossible, very wasteful, and also not very useful. But thank you for your question.
More questions? Probably I can ask one question. So in LM or so usually it's like human beings given a rate of scores. So in your proposed robot arena, so do you think it's better like for like Gemini, this kind of video language model or VLM to do the like to give the score or also using human to do the
Yes, so we are using humans right now. These are our humans. So this is what we use in the benchmark. The Gemini, we used it as a fast, cheaper way for us to do sanity check. We ask humans for preferences, and you can also ask them for absolute task progress scores, like how much of the task was obtained. Yeah, so ideally we want humans to do that. Now we are working on, because we are in simulation, you have access to the ground truth state, so you should be able to have ground truth reward functions. Yeah, so that also is something we're working on. Other questions? Yeah.
Real quick, you talked about using VLMs to get some of the physical properties like size and maybe weight. How well does that work in your experience?
Yeah. So the physics is incredible, is like absolutely amazing. And the size is also incredible. I think potentially these are very easy because they're just few numbers essentially. So it tells you, oh yeah, I think it's polyester and so on. And I think this is the, physics, etc. Apparently they know a lot about how the world works. Now, getting the shape out is something that the VLM cannot help you. That's why we have those tools, right? So there, unfortunately, we cannot rely on that. But yeah, I think the physics predictions are pretty fantastic. Yeah. Well, thank you for your attention and thank you for inviting me.